Hey there, guys. Here we go again with the um, logic circuits like you never seen before. Now, this method that we're using to build logic circuits is basically a programming language that we use for machine controls, and it's called ladder logic. Ladder logic, ladder logic. And in ladder logic, we're basically building what's called a very old method that's called a relay logic that represents the to control the signal traveling from the input or from the bus bar to the output or the coils. And we control it through relays. And these relays are either normally opened or normally closed. Normally opened represent the relay that turns on when the variable is on, when the parameter is on, and normally closed represents the relay that turns on when the variable is off, basically. And when we say turns on or off, it's basically a switch, and either that switch is connected or not connected, basically. And what's happening here is we're going to start after the last video where we did the basic logic circuits. In this video, we will do a little more complex logic circuits, and we will start with the half adder, full adder, multiplexer, and a decoder. These circuits are normally essential to the logic control, and the idea behind this video is to show you that these are actual signals that we may need in the future when we do circuit controls or even electrical controls. In some cases, if you look at electricity and how it's controlled, or airplanes and how they're controlled, or cars, how they're controlled, or machines controls, these all use what we call logic circuit or binary logic. And let's start with the half adder. The half adder basically is a circuit where we have two inputs and two outputs. One of the outputs is the sum and the other output is the carry. The reason we call it half adder because it only has an output carry. It doesn't account for the carry input that is coming from the previous operation. So this is an independent circuit that is basically half of what it should be. Now, we're going to take a look as usual that you've learned in school. You're going to build a truth table, and from the truth table, you're going to build the K-map, and the K-map will give you these guys right here. These are the formulas for every output. And with the half adder, we see that the S or the sum output is on or is 1 when only one of the inputs is on. And if we remember from the last session, that is the case for the XOR, and we know how to build the XOR. That's on, off, on, basically. And in this case, if I have only one or one and only one of the inputs on, S will be on. And then we take a look at the carry output. The carry output is basically saying only when both inputs are on, the carry output is on. And in this case, we have A and B, which is only when both are on. And that's the AND circuit. And let me just verify that this is actually what we're looking on. So if A is on, or A is 1, B is not, or 0, S is on, C is off. So that's this case right here. Now let's go the opposite. B is 1, C is 0, or A is 0. That's this case right here, and that is this case right here. And then both A and B are on. That will be the last case right here, where S is 0 and C is 1. Pretty straightforward if we look at it from the perspective of what is actually happening. And in here we say not AB, A not B. This is basically how we build this circuit. And then if we look at here, this is A and B turning C on. So we're taking those cases one at a time and then build them up here. Let's go to the full adder. It'll be a little more complex. And what the full adder is saying basically is that we are accounting for the carry input that is coming from the previous operation and generating the sum and the carry output. The full adder is basically a plus operation that accounts for three variables to be inputted, or three signals to be inputted. And what we're going to do is basically look at the final results. You know how to come up with the with these guys right here. I'm going to leave that for you. Now I'm going to show you how we're building this circuit right here. And basically what we're saying is S is on when 001. So I'm going to look for 001. You can see 001. S is on 010. Okay. That's 010. That's the next case. And then S is on when 100. That's 100. And then S is on when 111. And that's 111. Basically, that's what we do. And this will guarantee that in any of these cases, the signal will get from the bus bar to, or the main signal to the S to turn it on. And we'll test it later when we see how the C out is built. So we're gonna say C out is on when we have 011, and that's 0 1 1. Then C out is on when we have 1 0 1 1 0 1. That's the second case. And then C out is on when we have 1 1 0. That's 1 1 0 and 1 1 1, basically because of this. So we're gonna say C out is on when we have both A and B are on, and the C will be a don't care in here because it's either 1 or 0. So we say it's a don't care. And that's basically how we built and optimized the circuit right here. If you can understand this method, and if you can understand how we're basically conditioning the signal to go through a bunch of switches, and depending on how the switches are flipped, the output will be on. Uh, this is a very simple way for you to basically not need to memorize any of the uh, logic gates or any of the logic designs, because you will understand right away how it works and understand how things are going. So what we're going to do here is we're going to look at these circuits and basically go through them one at a time. So in here, we're going to say if any of A, B, or C is on while the others are off, S will be on. So that's A alone, that's S is on. B alone, S is on. C in alone, S is on. And then if all of them are on, S is on. Okay. And then we come to the C out. The C out is basically saying if we have more than one ones, the C out is on. So we have one, we have two, this is on. We have two, it's on. We have three, it's on. Basically it. And the easy way to remember the full adder is that add them up, man. Just add them up. 1 plus 0 plus 0, that's 1. 0 plus 1 plus 0, that's 1. 0 plus 0 plus 1, that's 1. 1 plus 1 plus 1, that's 3. And 3 is basically written as 1, 1. So that's 1, 1. And then what do we need to carry out is basically if we had more than one true signal. And that will be basically saying if A, B are on and C is off, if A, B are on and C is on, if A, B, and so on. If A, B are on, C is on or off, this will come out. If C is on and either A or B are on, this will come out. So that's basically it. So you remember, just add them up. Just add them up. And you'll find the results right away. Then we do the multiplexer. The multiplexer is a circuit that basically allows us to have a set of switches to pick one of the input signals to go to the output. And what does that mean? So S0 and S1, we call them selector switches or control signals. D0 through D3 are the inputs. And if I'm at S, or the selector switches are basically a number. If I'm at 0, 0, then D is in control of Y. Whatever D is, Y will be. If I'm at 1, D1 is in control. If I'm at 2, D2 is in control. If I'm at 3, D3 is in control. And let's test that theory. So right now I'm at 0. You can see if D0 is 1, Y is 1. If D0 is 0, Y is 0. And as we go, What do I need to make this on? It's basically turn S0 on, and that's what I'm going to do right here. See, this branch turned off and this branch turned on, giving the control to D1. So whatever D1, Y will be. Nothing else matters. And then same thing. If I do like in here, if I turn on S1, this branch will turn on, giving D2 the control. And if I turn both S1 and S0 and S1 on, this branch will turn on and giving the D3 control over Y. That's basically the idea. And it's a bunch of switches that are selecting which signal goes to the output. Then we look at a decoder. Decoder is basically having an output signals numbered in decimal, and then whatever that number, we build a set of input signals that are that represent the binary number. So if we have 4 outputs, I need 2 input signals to build the binary numbers from 0 to 3. That gives me the 4 outputs. So if I have a 0, 0, that's number 0. If I have 0, 1, that's number 1. If I have 1, 0, that's number 2. If I have 1, 1, that's number 3. So pretty straightforward, and what it's saying basically is this right here. So we count from 0 to 3 in the AB, and then Q0 is on only if both of them are zeros. Q1 is on when B is on and A is off, and so on. And they're basically counting up the number that we're building through, or we're triggering through the binary selector switches. This is the end of this session, and if you have any questions or comments, please leave them so we can address them in the next session and answer all your questions. Thank you.